sort of come together and figure out the intersection points between your two groups, if you will. So let's first hear from the group that worked on the no solution case. So Catherine and Jocelyn. So what did your system look like?
The lines are parallel to each other.
Okay. So let me see if I can recreate that here. All right.
It was 4y minus 3x equals 9.
Okay.
And 6x minus 8y equals 9.
4y minus 3x equals 9. And 6y minus 8x equals 9.
Mm-hmm.
And your graph looked something like this, although not exactly the same, right? Because your sliders and mine are in slightly different position. So you said that this was no solution. And by the way, because the terminology exists in the book, and we may call upon it again, yeah, exactly. A system of equations which has no solution is called inconsistent. So you had here an inconsistent system of equations, and you can tell graphically because, how did the picture tell you that?
I don't know, because they're parallel to each other and they never intersected.
Ah, okay, so two things. Parallel, first of all, and according to Euclidean geometry, the postulates of Euclidean geometry, two lines that are parallel have how many intersection points in the plane? 0, if they're not the same line. Right, so that's why the second part of what you said is important. Right, so we need to know that they're parallel and that they are not what we would call coincident. Right, they don't lie one on top of the other. Okay, so let's take that parallel observation for a second and look back at the original equations. How could we have known from the two equations that we have listed here that these two lines are in fact parallel?
By just looking at their slopes.
Yeah. Okay. Right, let's think about, I must have copied something wrong up here. 4y minus 3x equals 9. And can you read off your second equation again?
6x minus 8y.
Yeah, I had my x and y backwards. I knew something looked off. 6x minus 8y equals 9. Okay. All right, so how could we have known? Let's take both of those equations and find their slopes. After all, standard analytic geometry tells us that two lines that have the same slope are definitely parallel. So what was the slope of 4y minus 3x equals 9? If we solve this for y, we get 9 plus 3x all over 4. And if we solve the second equation for y, so I'm going to kind of write over some stuff here, we get 9 minus 6x all over negative 8. But what's the slope of that second equation? Where do we find the slope of the equation y equals 9/4 plus 3/4 x? 3/4. It's the coefficient of x once we have it in this standard form written this way. Actually, not standard, the slope-intercept form. The slope of that equation is 3/4. And likewise, the slope of this first equation, negative 6 over negative 8, the coefficient of x. But that's the same thing as 3/4. So our two lines have the same slope, and therefore they're definitely parallel. And how can we tell that they're not the same line? They have different y and x intercepts, right? In particular, the y-intercept of the second line is going to be the coefficient, the constant term, okay, in slope-intercept form. And the intercept, therefore, is 9/4 for the second equation. But for the first equation, what's the intercept? Whoops. 9 over negative 8. So the fact that the slopes match tell us that the lines are parallel. But the fact that the intercepts do not match tells us that the lines are not coincident. There's the analytic geometry viewpoint on this whole thing. Well, what I actually want to do for a second is return to this system of equations one more time. And instead of thinking about it from a slopes and intercepts perspective, let's strip it down to its bare essentials and forget about y's and x's and the right-hand sides and equal signs, and let's just turn everything into coefficients. And here's what I mean by that. There we go. So to turn everything into coefficients, let me take our equation once again. 4y minus 3x equals 9, and 6x minus 8y equals 9. And I'm going to take that first equation and rearrange it so the x's come before the y's again. And mathematically it's meaningless, but for the sake of the way that we're going to organize our equations this semester, the distinction is important. So the negative 3x will come first, and the 4y will come second. Okay. Now I'm going to boil away all the x's and y's and equal signs and take just the coefficients out of this. So I'm going to have negative 3, 4, and 6, and negative 8. And then on the right-hand sides, I have my 9's. Because these numbers, these coefficients, are what's really important in this whole process. The x's and the y's, yeah, they just sort of come along for the ride, right? But really, when we make all of our choices in how to solve in a system of equations like this, we're making those choices based on these numbers, the coefficients, not on the x's and the y's. I'm also going to take the liberty of putting a little vertical line here just to kind of separate those numbers that are coefficients of variables and those numbers which belong on the right-hand side. And in this process, what I've created is called an augmented matrix. For this system of equations. And now that it's been arranged in this fashion, can you find another way to convince me that in fact these two lines are parallel? What's a way of getting at the slopes here being the same without having to find what the slopes are? Can you see any relationship between these two rows? So in anytime we translate things into a matrix like we just did here, each of these rows came from one of the original equations, and each of the columns came from one of my variables. So is there anything particular about the relationship between the rows of this matrix that could tell us that we have two parallel lines? Can you spot it?
Just observation that where the left of the augmented matrix, negative 2 times the top.
Yeah, let's forget about the right-hand side for just a second.
That's the negative
And look.
2 times the top row is just the bottom row.
Yeah, does everyone see that observation? If we look at the first row and the second row, the relationship between negative 3 and 6 is that the latter is negative 2 times the former. But that is the same relationship that exists between 4 and negative 8. So the entire second row is negative 2 times the entire first row, at least if we forget about the right-hand sides for a second. And so what we find out, I'm just going to write that observation over here to record it for posterity, that row 2 is a multiple of row 1.
Subtract 2 times it.
Yeah, so that was going to be where I'm going next with this. That now, when you went to solve this system of equations, when you went to solve it by elimination, what did you do? So you had this system of equations, and it had x's and y's in it when you solved it. I mean, I stripped them out, but...
Multiply the first one by 2.
Right, so when you went to solve this equation by elimination, let me write down the steps that you took. First, you multiplied the first equation by 2. And when you multiply that first equation by 2, negative 3 became negative 6. 4 became 8. And 9 became 18. Right? So that was the first step, is you multiplied by 2. Notice that's the same 2 that described for us what multiple the second row was of the first. Right? Negative 2 times. And then once the first equation was multiplied by negative 2, then what did you do? Right. Now that you have the setup such that we can eliminate one of the variables by adding, we decided to add row 2 plus row 1. So let's do that here, just as a kind of a third row, if you like. If I add negative 6 plus 6, I end up with 0. If I add negative 8 plus 8, I end up with 0. And if I add 18 and 9, I get 27. So those were the two steps. You multiplied the first row by 2, then you added the result to the second row. And what we got was, in our matrix formalism now, a third row, both of whose first entries are 0, and whose last entry is 27. And this corresponds to what equation that you found along the way of solution. What did this look like on your paper?
0 to 9.
Right. You had 0 equals 27, the suspicious-looking equation, 0 equals 27. Right. But this is not an abstract algebra class. We are not playing fast and loose with the integers. 0 and 27 are definitely different things, at least within these four walls for today. So you made the observation, actually just now, in what you said. These two are not equal, in fact. And therefore, following the conclusion logically here, in order to accept the premise that there exists an x and a y that solve both of these equations, would force us to also accept the premise that 0 is equal to 27. And since we cannot accept the premise that 0 is equal to 27, we cannot, therefore, accept the premise that there exists an x and a y that solve both of these equations initially. Right? In other words, if this first statement is true, then this second statement must also be true. But the second statement is not true. Therefore, the first statement cannot have been true. Now you're hearing the bells of Math 180 kind of ringing in the background, right? If P is the proposition that there exists an x and a y that solve both of these equations, and Q is the proposition that 0 is equal to 27, then, because of the steps that we took to get from there to there, P must imply Q. There's no way around it. But Q is a false statement. Therefore, P must be a false statement. It's the contrapositive, right? If P implies Q, then the falseness of Q implies the falseness of P. If every time I take an umbrella with me, it's sunny, then if it's not sunny, I must not have my umbrella. Contrapositive. So in other words, that's the logical explanation for why arriving at an equation that looks like this, 0 equals 27, means that our original system of equations had no solution. Because if it had a solution, it would force 0 to equal 27, which it doesn't, at least not for us. So other group, how was this similar? What happened to you along the way that looked the same as what happened here?
When we did substitution,
Mhm.
we got rid of the variables.
Okay.
Same as they did, but except we had 0 does equal 0.
Aha. So what was your system of equations, out of curiosity?
It was 4y minus 3x equals 2,
4y minus 3x equals 2.
and then 6x minus 8y equals negative 4.
Okay, so here was their system. Let's rearrange it in the way that we were accustomed to rearranging it. So let's get the x and the y in the same order on the top. So help me out. This was negative 3x plus 4y?
Yes.
Okay. Okay. And so if we were to then put that into augmented matrix form, let's try and reproduce this as best we can here. Then I would have negative 3, 4, 2, and 6, negative 8, negative 4. All right? Then the very same step sets up the elimination as set it up for the other group. Right? Multiply the first equation by 2. 2 times. And if I multiply the first equation by 2, this becomes negative 6 and positive 8, and this becomes positive 4. And then, again, same step as the other group. Let's add those two equations together. I get zeros on my left-hand side, but now I get a 0 on the right-hand side.
Means that the y intercepts are the same as well as the slopes being the same.
Right. So now we end up with this equation 0 is equal to 0, which is a proposition we can accept, right? That is definitely a true statement. So from your picture, what was true about the picture of these two lines?
It was just 2 lines on top.
It was 2 lines on top of one another. You couldn't even tell the difference between the two of them because they were exactly on top of one another. So what's interesting about this example is how, and this was the conversation that we had in your group off to the side, is that it's a little harder for your group now to describe what are the solutions of this system of equations. Because there's infinitely many of them, how do we write infinitely many different solutions down on paper? It's easy enough just to write no solution if there's no solution, or just to write the single-ordered pair that solves the equation if there's a single-ordered pair. So what did we come up with here?
If we're looking at the solution to be the intersection of the two lines, since they intersect at every single point, we can just express an equation for the line that they both share, and that would be the solution. That would be an equation for the solution.
Right.
The solution is just the line.
Right, because any ordered pair x and y that solves one of those equations will also solve the other. Oops. And so one way of doing this, one way of expressing the solution when we've arrived at 0 equals 0, which means now we have infinitely many solutions, is to just write the equation for one of these lines by itself. And an equation for that you could find, for instance, by solving one of them for y. So you solved the first equation, I believe it was, for y. It doesn't matter because they both describe the same thing, right? But if we solve the first equation for y, you got y is equal to
1/2 plus 3/4 x.
plus 3/4 x. But then the second equation is just going to tell us the same thing. All right, it's going to give us exactly the same thing if we solve it for y also. So one way we might choose to represent this system is by saying, well, if this is what y is in terms of x, then all we have to do now is to say what x is. And x is whatever the heck we want it to be. Right? We can pick any value for x because that's just going to pick out one of the points along this line, which is the two of our equations on top of one another. So we might just write x is equal to x. Maybe put a little curly braces around this and a comma or something like that. And that now describes an entire set worth of infinitely many different solutions. To get a single point out of that, we have to choose a value for x. For instance, if I choose an x value of 0, then the equation over on the right tells me what the value for y that corresponds to that is. It's going to be 1/2. And this is a single point which belongs to that solution set, but there's infinitely many others, right? Because I can choose any one of infinitely many other choices for x. And every different choice for x is going to give me a different value for y that corresponds to it. And this, because a solution exists to this system of equations, we're still going to call it consistent. So inconsistent is the case where we have no solutions. Consistent describes any situation in which some solution exists, whether that solution be a single one or whether it be more than one. So I want to close with this thought for today. And that is, if I can find a blank screen here. Where is my blank screen?
I think you should just always have by default a Mathematica.
Well, I do. Here it is. So the question I want to wrap up with today is, how many solutions may a linear system of equations have?
You mean 2 by 2?
Well, I mean, we can start thinking about 2 by 2.
Yeah, well, I mean, it depends on.
So what are the options? based on the examples we've seen today. So the first example, the one that I worked, how many solutions did that have? That had a single solution, 1. And in that case, we say that that solution is unique. Unique is an important and special word in mathematics. 1 unique solution. And in a picture, that's just the picture where both of our lines happen not to be parallel, because 2 lines that are not parallel intersect in one and only one point, in Euclidean geometry anyway. So that was the first example. But then the examples that you all worked rose what other possibilities? Many solutions. In fact, how many solutions did your... Right. Infinitely many solutions. The case where our 2 lines happen to be one right on top of the other. And the other example, none. Where we have 2 lines that are parallel but not coincident. And so that's a complete classification of the nature of the solutions of a 2x2 system. It has to be one of these 3. Either we have no solution at all, we have infinitely many solutions because the lines lie on top of each other, or we have one exact unique solution that's only one place where the 2 lines cross. But as we'll see this semester, it turns out that this is true not just for 2x2 systems, but for all linear systems. Are either going to have one solution, infinitely many solutions, or no solutions. And just to break out the terminology one more time, these 2 cases, one solution and infinitely many solutions, those are the consistent cases. The no solution case is still inconsistent. And then the uniqueness is the only thing that differentiates the 2 of these first cases. Where there is one solution and only one solution, we say that solution is unique. When there are infinitely many, we just say that the solution is not unique. But the fact that this does classify the solutions of all systems, regardless of how many equations and how many variables, is something that we're going to take kind of the rest of the week to explore that gray area. So what you'll do in the homework this afternoon